We left off about here, and in these discussions or comments on morphological crystallography, there are a few more things to say, and then we'll move on to actually looking at visible light and X-ray diffraction, and in the context of that paper I sent you from Scientific American, Lawrence Bragg's description of the basics of crystallography, which I think is a beautifully written piece. It shows what the school education of an English boy led to in terms of writing ability. It's really quite something. Okay, so we considered a number of these illustrations of lattices, remembering that in all of these illustrations, the little dots or balls at lattice points are just representing that, lattice points. They aren't intended to represent atoms or molecules. There would be atoms or molecules perhaps at or surrounding the lattice points, but right now we're just worried about the periodicity of the three-dimensional lattice. And so we looked at the process of labeling the faces of crystals with respect to the lattice planes that compose them in terms of the intercepts of the faces on the three crystal axes. And the particularly simple cases are the cubic ones illustrated here. And then we talked about the difference between actual and virtual lattice planes. And Tom raised a question about, I can't remember which one. I think he raised the question about, one of these days I'll learn to use this. About this case here, where we were looking at the 2, 0, 0 planes. And I said that that is a case of composite indices, a case of virtual lattice planes, because there is a common factor of 2. So some natural number that is a factor of this for the three indices, the greatest common divisor. Right? So whereas the 1, 0, 0 planes are actual lattice planes, the whole family of parallel 1, 0, 0 planes would pass through all of the infinitely many lattice points in our idealized cubic lattice. So those three indices are co-prime in the sense that there is no common factor greater than 1, no greatest common divisor. So these sets of planes are labeled in that way. And there can be, of course, infinitely many lattice planes in a set. Okay? So here we have depicted the 1, 3, 4 family of lattice planes. And all of those are actual lattice planes because each of these members of the family pass through all of the lattice points in the lattice. So you will be, when you get to talking about your X-ray diffraction data, each of the spots that you measure on the film will be characterized by an integer triple, and you will in fact label some spots 100, and then along that same direction you would find a 200, 300, 400, and so on. So those higher index planes that are parallel to the 100 primitive set are virtual lattice planes, and what the common factor represents in those cases is the order of diffraction. So we could measure diffraction from the 100 plane and then planes and 200 planes, and what this 200 reflections represent would be the second order scattering from the 100 planes. So it's only the lattice planes that are scattering. These in-between planes are not lattice planes, and so the order of the scattering gets incorporated into the indices. So we would measure second order scattering from the 100 planes and label that the 200 reflection, which occurs at a higher scattering angle. The order of scattering, as we'll see with Bragg's equations. With increasing order, there's increasing scattering angle. And then we played with this little exercise. So the point that we should have made last time, or when we missed on Tuesday, was that these lattice planes, these families of equally spaced or parallel lattice planes, become the faces of a crystal. So here we have a point lattice, a parallelogram point lattice whose repeat distances are shown up in the corner, an A repeat and a B repeat. Right? And then these various lattice planes drawn through the points, just a few examples, drawn through the points of the lattice. So what we have here in the case of this family of planes with spacing, interplanar spacing D1, notice that's the perpendicular spacing between parallel planes in this lattice and not the translational repeat A. Right? So D1 is not equal to A because of the parallelogram shape of this lattice. And so we look at the labeling for these three families of planes. These represent the family 100. Over here, this slanted family represents the set of planes 130. Now, how does that arrive? We pick any lattice point as an origin, say this one, and then look at the adjacent lattice plane in the family. Where does that adjacent plane cut the A and B axes? Well, it cuts the second plane here, cuts the A axis at unit translation along A. And then it cuts the B direction here, here, and then a repeat. Okay? So 1, 2, 3 intercepts along the B direction. So this is the 130 family of planes. So we're looking at the intercepts on the lattice axes. If we choose a different set of lattice axes, as we saw we could, we'd get a different set of indices, but they could be systematically converted one to the other. And this third set, which is sloping in the other direction, right? Where do the planes here intercept the axes? Well, the second member of this set, if we take this this lattice plane as an origin, the second member cuts the A direction at unit repeat, but then it cuts the B direction at half unit. If we're taking this guy to be the origin, then this second plane is cutting at half of the repeat along B. Okay? And the difference in the slope, between this family and this family is denoted by giving a negative index. All right? So we have the minus 1, 2, 0 family. Now, one generalization. Yes, sir.
What's they're showing like a vector for H1, H2, H3. What is that supposed to?
Okay. That's the plane perpendicular. All right. So these planes could be crystal faces, this 100 set, and this would be the direction of the normal to those planes. And if we were measuring the interfacial angle between this family and this family, it would then be the angle between the vectors H1 and H2. Translate them to a common origin. Yeah? So generalization we can take away from here is that the higher the indices, the shorter the interplanar space. Okay? So these guys have a larger interplanar spacing than these guys, or these guys. Okay? And in this case, the H3 set planar spacing, perpendicular distance between members of the family of planes. And then the other generalization we can make is that within these families of planes, the higher the indices, right, the smaller the interplanar spacing, and the lower the reticular density. What do we mean by that? It's if we consider any one of these planes, consider the density of lattice points in that plane. Right? So the lattice points are getting more widely spaced as we go to the higher indices. So these are more examples of the same thing, and you can stare at these slides and reach the same conclusions with respect to how the families of planes are generalized with respect to despacing and reticular density, and with respect to the negative indices associated with families of planes that are differently sloped. So these, by the way, I'll get these slides up on the FTP site, I hope this afternoon, if not, certainly tomorrow morning, or tomorrow sometime. Okay, so here's an illustration on that same point lattice of what might be the faces of a crystal, which is outlined in shape. So it would be bounded by faces 1, 0, 0 and minus 1, 0, 0. Okay, so if this family of planes is cutting the A direction at unit translation along the A direction, as indicated here for the cell, then these guys are cutting along the negative. This family is cutting along the negative A direction. So we have these parallel bounding faces for this crystal. You won't always, not always will it be so that the bounding faces of a crystal, even a nicely grown crystal, I'm not talking about one that's broken or stuck to the slide of the vessel or so on. There won't necessarily always be faces that come in parallel pairs, but in this case, yes, 100 and minus 100, and then 010, 1 bar 30, and 1 2 bar 0. So we could have a crystal of this shape. It would be, its faces would be labeled as indicated here. And so it's the interplanar spacing that defines the indices, but we might have quite a sample of parallel planes that compose the crystal. And certainly a crystal that is only, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 unit cells. That's a tiny, tiny crystal. Unit cells, even for big molecule crystals, are little things. This is an illustration again of this relationship between the Miller indices and the reticular density. So we're considering the case of a simple cubic packing of lattice points or entities building up the crystal. So here are this is the arrangement for the 100 face of this hypothetical crystal, okay? But then the 210 face would have lower density of points on it, and you see that the next layer back would be recessed. The 110 is an intermediate case, so lower density of points than here, higher density than here. So again, the higher the indices, the lower the density. So the generalization is that the bounding faces of crystals will be consist of families of planes. We've built families of planes with small Miller indices, and the larger interplanar spacings, and the higher reticular density of lattice points or atoms or molecules or whatever you're thinking of the crystal as being composed of. Okay, so these are more illustrations that indicate how we deduce Miller indices with respect to the intercepts that the planes make on the lattice axes, and then also an introduction to the notation for defining directions with respect to the lattice axes. We designate them in square brackets, right? So here's indication of the 1, 1, 0 direction with respect to this rhomboid-shaped crystal, and here the negative 1, 0, negative 1, 1, 0. And then the notation is parentheses around the labels for the Miller indices defining for the plane. And when you get these slides, you can then satisfy yourself by looking at the intercepts of these different Miller index planes that could be bounding faces for a cubic crystal. So the underlying pattern is a cubic one, but we have here a cubic crystal with its faces, beveled faces, here along an edge, here at a corner, and so on. And then the corresponding labeling of the planes that represent those faces. Here another example of the same thing, and another example of how the algebraic sign of the index matters with respect to the direction in which the planes slope, and more of those kinds of examples. So here's a simple case where we're considering the buildup of a crystal of this shape in terms of the lattice planes that designate its faces. So here we have a simple cubic lattice with these end faces, a side face, and a top face, A, B, C, okay? And with respect to the crystal, there's the C face corresponding, the A face corresponding, and the B face corresponding. And then if we consider these sloping faces, I will start up here with B. So this is a family of planes which cuts the A direction. Now remember, we're looking at little cubes here, so 1, 0, 1, 0, a simple cubic case. So this then cuts the A direction at unit length and the B direction and the C direction at unit length, and then is parallel to the B direction. There's no intercept. So the faces labeled T are the 1, 0, 1 faces, and in the same way, the faces labeled Q are the 1, 0, 2 faces, and the 2 comes about because we're cutting the one direction at half the repeat distance. Okay, here we're cutting the vertical direction, C direction, Z direction at half a repeat to compose that nice looking little crystal for some cubic substance. And more of the same thing here. So it's worth digesting the content of these illustrations, and who knows, they might even turn up on a midterm exam for you as an exercise for you to work out the indices. So another important property of crystals, some crystals, is this business of enantiomorphism. So there's a rightness and a leftness to some kinds of crystals depending on their symmetry. If they are non-centrosymmetric crystals, we can have these left and right versions of the crystal. I forgot to bring them along. I'll show you in a minute. So here's just a line drawing of the same thing. And the indices of these various faces, labeled R, M, S, and so on, have been worked out years ago very carefully. And so the set M, that surround the crystal parallel to the vertical axis, have all been worked out, a family of them going around the crystal, M, 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 and so on. So this is a trigonal crystal, has hexagonal symmetry, or trigonal symmetry, and hence there's a fourth index gets introduced. We're not going to worry much about indexing. This is what I forgot to bring along. I have a pair of natural crystals, about like that, so-called Herkimer diamonds from Herkimer, New York, over along the Erie Canal, but it must be 3 or 4 hours away east from here. And so here you see a left one and a right one, and I have a pair that are not as perfect as this, but are clearly left and right. And you identify what's left and right by looking at these little facet faces. This one, going up to the right, and this one going up to the left. So you can, I'll try to remember to bring them along, and you can play with this pair of crystals and see this. Here, the same kind of illustration, and here you can see the left and right handedness of this pair of quartz crystals. So Vladimir Bragg is the guy responsible for all the R and S designation of enantiomorphic crystals, and for his work in stereoisomerism. He got the Nobel Prize in chemistry in 1975. I was going to say mid-70s, in 1975. And this is an illustration from his lecture of a left-handed and right-handed quartz crystals. And in working through this nomenclature, it gets a little bit sticky. So left-handed quartz is dextrorotatory. The plane of polarized light passing through one of these crystals gets rotated to the right by a left-handed crystal, and vice versa. So figuring all that out and keeping it all straight is one of the reasons that Bragg got a Nobel Prize, and systematized this for all of the generations of organic chemistry students to follow. Historically, the great historical event in systematic stereochemistry, optical activity and stereochemistry, was Louis Pasteur's observations on sodium ammonium tartrate crystals. Tartrate crystals, you see them, they're beautiful in a bottle of wine where things have crystallized. And so again, the leftness and rightness, and Pasteur was patiently looking at these crystals under a microscope and separating them into left and right, and then dissolving them and looking at the optical rotation of polarized light passed through the solution. So this was an important chapter in three-dimensional understanding of three-dimensional stereochemistry. So then there's an amusing story connected with this. Unfortunately, my friend David Langs is now emeritus scientist here at the Institute, but maybe you've met him. Very, very interesting character, wonderful to have a conversation with a very unusual way of thinking. He's one of those minds. He's a guy, for example, who loves solving puzzles of various kinds. He worked on direct methods of phasing, and he was like a numerologist looking at these questions of how to relate the phases among families of amplitudes. That's a diversion. But anyhow, when Dave was a beginning graduate student, he was given the problem of looking at copper acetate crystals. I don't know if you remember copper acetate from your chemistry course, but it's two copper atoms that with bridging acetates, and there are four of them bridging a pair of copper, so it's like a paddle wheel structure. And Dave's PhD professor at the time, he was a new student with this professor, had noticed that he thought he saw left and right versions of these crystals in a petri dish and so on. So he set Dave to work on looking at what could be the optical activity properties of the wagon wheel structure for copper acetate, binuclear copper acetate. And so Dave is patiently sorting under a dissecting microscope in the petri dish, left, right, right. And he's at this for quite some time because they wanted to get a macroscopic sample of each kind of crystal to dissolve it up, look at the optical rotation, do all kinds of spectroscopic studies and so on. And then Dave had a twitch when he was moving one of these crystals, and he happened to flip it over, and it turned from left to right, or right to left. So it was a whole misguided undertaking from the beginning, and until you jiggled a crystal that caused it to turn over. So then he went on to a different project. His telling of the story is much more interesting than mine. Okay, so this is an Escher drawing to put in mind the notions of leftness and rightness. And here, a digest of an exercise of going through and figuring out the Miller indices of the systematic way to deduce Miller indices of the faces of a crystal. It's a pretty tedious exercise. It can be a very tedious exercise, especially if the crystal has many, many faces, many facets. Okay, so we had looked at this notion of that the indices are always going to be small whole numbers. The faces of a crystal will have indices that would stand in the ratio of small whole numbers. That was René Just Huy's observation. Here's a simple illustration of it, and an illustration of how, from measuring the interfacial angles, we can deduce a notion of the relative dimensions of the unit cell. Okay, so we're imagining that we're looking down the A direction, and the angle between what we've labeled the 0,11 face and the 0,10 face is measured as theta, okay? And that means that this angle is theta. If we've chosen two edges of the crystal to be defining the directions of the unit cell axes, then we can then deduce what are the relative lengths. Can't deduce the absolute lengths because we're looking just at the interfacial angles. But we can guess the ratio of B to C and A to B and so on. So we can get relative lattice dimensions. Here illustrating again how such a calculation is done, looking at the angles between the 3 and 4 faces. That will give us a way to estimate the ratio of the A to B lattice translation ratio. The tangent of half that angle gives us a picture that with these little parallel rectangular relative unit cell directions. Dimensions, sorry. All right, so there was a simple case of the primitive way of measuring interfacial angles. That meant you had to have crystals big enough to hold in your hand. But if you've got only tiny crystals that you can't be manipulating around by hand and measuring with a contact protractor. This was a device that became standard. So you've got the possibility to rotate all of this around about a vertical axis, okay, which would pass through the center of this larger circle. Then we have a horizontal axis, which allows rotation of this goniometer head that bears the crystal here. So here we are imagining we have a crystal mounted with respect to this rotation axis. And we can observe that crystal through a microscope when it is illuminated by a beam of white light. And so we can measure then the angles by looking at when do we see the reflection off the crystal face. So we get a reflection off a crystal face, we rotate about this axis until we see the next reflection. All right, now we have measured an interfacial angle between the faces that gave those light signals. And so this instrument, this optical goniometer, was used in many laboratories, many laboratories in Europe. It was the classical way of doing crystallography before X-ray diffraction. And the results were recorded by plotting. So here we're looking at this constellation of face normals from this kind of beveled edge cubic-shaped crystal. And then we project them from one pole onto the upper hemisphere. We get diagrams like this, where you can't read them here, but these are labels for the faces responsible for that have these face normals. And that's all plotted on a stereogram, or can be plotted on a stereogram. And that was done for thousands of substances. And von Groth systematized all this in 1888, in this 5-volume work. It sits up on the shelves in the library here. It's worth paging through to see the kinds of conclusions that people were able to draw. Systematic chemical crystallography. And here's an example for orthorhombic sulfur. I chose orthorhombic sulfur because one of my jobs as a postdoc was to not do the optical crystallography, but do X-ray crystallography. And the specimen crystal I had of sulfur was pretty much that shape, although tiny compared with these. And hence I chose sulfur as an example. So we look at the entry about sulfur in Groth's chemical crystallography. Very hard to read because of the way this is. But in any event, the measurements of the interfacial angles led this Bragg, I think Czechish, to conclude that the relative, that first of all, that it was an orthorhombic crystal, okay, so that we had a triple of mutually perpendicular axes, and their lengths were in this ratio, 0.8 to 1.9, to 1 to 1.9, if I'm reading that correctly. Okay, so given this relative dimensions of the unit cell, Bragg did an experiment to sublime sulfur and ended up with this very multifaceted crystal, but he was able then to measure all those interfacial angles and label with Miller indices all the faces of this multifaceted crystal. He also did experiments where he obtained crystals from sulfur dissolved in carbon disulfide and in chloroform, and I can't remember, I can't read what the other one was. And so he got these sulfur crystals of quite different shape, but of course the same interfacial angles. And this was all done in, 1869, thank you. Failing eyesight. 1869. So this was done then for thousands of substances. The compilation that Groth put together is in 5 thick volumes upstairs with this kind of detail for almost any crystalline substance that was available at the time. No protein crystals, of course, at that point. The first protein crystals were observed, I think at the end of the 19th century, by a German, Hinnefeld, I think his name was. And what happened, he was a biologist. He was working with some kinds of earthworms, and he had a smear of this earthworm blood between a pair of microscope slides that he'd been looking at this blood sample. And of course, in time it dried up, and out came crystals. Right? So the first protein crystallization was worm blood, a protein from worm blood between 2 microscope slides. Okay, and then so von Groth then took all those observations from this guy, Brezina, and compared them with other observations, a smaller sample of observations from other workers, and was able to draw conclusions about how this sample corresponded to these other guys. And again, this is the constancy of interfacial angles, right? So these were also sulfur crystals, maybe with quite different faceting and size and shape. Okay. And this is just a reminder that as beautiful as these crystals are, and as patient as people were in using that optical goniometer to measure the interfacial angles, index the faces, and deduce the relative lengths of the axes. Crystals are not perfect things, and those of you who do protein crystallography will encounter the phenomena of mosaicity and twinning, because there are always these imperfections. These are atomic force microscope images of some protein crystal. I've forgotten what. Oh, here, glucose isomerase, about which Eddie Snell and Kristen Wunsch, Kristen, married name is gone for the moment. Her maiden name was Wunsch. In any event, about glucose isomerase, those folks know a huge amount because they did very detailed studies looking at radiation damage effects in measuring X-ray diffraction data on glucose isomerase. And we get these 2 common forms, these step structure or spiral structures on the surface of crystals. And here we're at higher magnification, seeing these little lakes of molecules packed together, and you see the growth going, and it tends to want to go along an edge. That's what these little arrows are saying. So in this direction, we have some growth that fills out this piece here, some enlargement of this piece of the structure. These are pictures from Alex McPherson, who used to spend summer times with us. He's professor at UC Riverside or Davis, now I can't remember, but a world expert on growing protein crystals. Okay, so this is as much as I wanted to say about the crystal morphology stuff. I'll get these slides to you at the beginning of next week. You can play the game of trying to index some of those planes on the line drawings and so on. Now I have to get out of here. Show. To here. and begin at least to in 32. Oh, okay, it's only 11:15, so we have some time to talk actually about X-ray diffraction crystallography, with the benefit of the background reading of that scientific American article by Lawrence Bragg. Bragg was just a kid when he figured out Bragg's law. He was a beginning graduate student at Cambridge at the time, and after let's get into the history here. So X-rays discovered in 1895 by Röntgen. We talked about this stuff in the one Thursday morning meeting this summer. I mean, did you come over did I remember to ask you to come over for the Thursday morning meeting? This was back in July, wasn't it? Sometime. No? Okay, well, you can breeze through the history on these slides. So Röntgen discovered X-rays and showed that you could have X-ray pictures of a skeleton. That was one of his first examples, taking X-ray of his wife's left hand. She decided never again because she thought it was really spooky to see her own skeleton. And so when he improved the technique, he had to turn to his colleague in the biology department who was willing to be exposed to the X-rays. So 1895, X-rays were discovered. Von Laue and his young colleagues, Friedrich and Knieping, showed that X-rays would be diffracted, form diffraction interference patterns with crystals, and then soon thereafter, the Braggs, father and son, deduced the first crystal structures. And Bragg the younger, figured out Bragg's law. Okay, what is that about? Well, this is the story of the discovery of X-rays. A graduate student, nearly finishing his thesis writing for his PhD in Munich, and working on a project about the interactions of visible light with crystals, concluded that if, as was thought at the time, was beginning to be understood, if crystals are composed of periodic arrangement of atoms, the spacings between atoms and therefore the dimensions of the units of structure, I mean, he had in mind these notions about crystal structure that had been postulated by Hui. So these spacings ought to be on the order of an angstrom, 10 to the minus 8 centimeters. And that could be deduced by considering the molecular weight of the substance, the atomic mass unit, the Avogadro number, and the mass density of whatever substance you're looking at. Form this expression, take its cube root. You get an estimate of the basic spacing, the unit spacing within the crystal. So Paul Peter Ewald had this notion about the internal structure of crystals, but he had some other questions about the development of his dissertation, and he went to consult with Professor von Laue, also in Munich, and when hearing the story that Ewald had to tell, von Laue concluded, well, if X-rays are waves, which was at that time a hotly debated issue, what are these X-rays? Is this a stream of particles that are being emitted from the cathode ray tubes, because that's how they were discovered? The radiation from cathode ray tubes exposed a photographic plate that was in the dark in a desk drawer nearby. That was the root of Röntgen's discovery. But then the question was, okay, is it a stream of particles, or is it a radiation that consists of waves? So von Laue said, well, if the X-rays are waves and the spacing is like this in crystals, then crystals should produce interference and diffraction effects with X-rays. And so his young assistants carried out the experiment to see if diffraction effects, interference effects would occur, and in analyzing their results, they came up with the famous set of Laue equations for X-ray conditions for X-ray diffraction, where these are the repeat distances of in a crystal lattice, A, B, and C. Nu and mu are the angles of incidence and scattering from corresponding to these directions, okay, so nu1, nu2, nu3, and so on. And the condition was that for interference effects, we should have those be, they should evaluate to an integer number of wavelengths. And sure enough, the HKLs here turn out to correspond to those HKLs, the Miller indices of crystal faces, even for the whole set of families of planes, whether they form crystal faces, visible crystal faces or not. So this was a paper that Herb and I wrote some years ago for 75 years of X-ray diffraction and crystallography. Now we're at 100, so I guess we wrote this 25 or so years ago. This is the apparatus that von Laue, Friedrich, and Knieping used. Here, like a Crookes tube, a cathode ray tube, where a beam of electrons was directed onto this piece in the center, which is a metal target with a sloping face. Off that face come the, well, actually, in all directions come the X-rays because of the collisions of the electrons with the atoms, excitation and then relaxation events, outcome the X-rays corresponding to the various energy level differences in the atom. Through a pinhole in a lead screen, over here, an optical goniometer borrowed from the mineralogy laboratory on which they could mount a crystal. They also got from the mineralogy lab a crystal of copper sulfate, probably on the order of 1 centimeters in size. And this was what happened when they exposed that crystal to X-rays. Not a very impressive diffraction pattern, but remarkable in that the beam of X-rays, which passed through an aperture in this lead screen, would have just darkened the center of this photographic film if nothing had happened. But there were these other beamlets that went in directions away from the beam direction, so that means that there were scattered X-rays. The crystal scattered X-rays. Because it was a biggish crystal, these were not a very highly resolved diffraction pattern. So, it didn't occur, it immediately occurred to him, well, we should try a smaller crystal and refine the apparatus a bit more. And when they did switch from large crystal of copper nitrate to a smaller crystal of zinc sulfide, zinc blende, they got these beautiful diffraction patterns. The zinc blende is a cubic crystal, and so if the cubic crystal was oriented on this optical goniometer such that it had a 100 or 010 or 001 face perpendicular to the X-ray beam direction, you got this fourfold distribution of scattered spots. So the face of a cube, perpendicular to the face of a cube, is a fourfold axis of symmetry. And then if they use those adjustments on the optical goniometer to reorient the crystal so that the body diagonal of that cubic crystal was along the X-ray beam direction, then indeed you get this threefold distribution of diffraction spots. So the diffraction followed the externally observable symmetry of these crystals, these zinc sulfide crystals. And so it is for other substances as well, of course. They did things like, in the initial experiment, grind up that copper sulfate crystal and see, oh, well, you turn it to a powder, we still get a diffraction pattern. There's this scattering away from the center of the film. If we take, again, a single crystal piece and move the detector film, the photographic film, farther away from the crystal, then that kind of collapses the diffraction pattern toward the center. If you move the film up closer to the crystal, then you kind of expand or enlarge the diffraction pattern.
Is it related to the resolution of the X-ray diffraction?
The resolution with respect to the internal structure? Well, sure, but at that time they didn't know, right? So we're looking at, in this case and these two cases, diffraction pattern from the same crystal specimen, the only difference being the film that records the diffraction pattern is further from or closer to the crystal specimen. So the resolution of these diffraction patterns, it's a scaling factor. These two patterns have the same resolution with respect to the interatomic spacings within the crystal, but different resolution on the film. And that's one of the things we'll come to be doing is calculating the internal resolution from what we record on the film, knowing the crystal to film distance and the wavelength of the X-ray. So there's a simple diagram of the experiment, idealized diagram, but the principle is there correctly.
Question about that
yes,
figure?
Sure.
So you said that the shorter spaces between the crystal and the film produce more dispersed patterns, larger patterns?
Right.
But wouldn't that...
So you imagine... Go ahead.
Picture you're seeing there. It seems like if you move the film back, you'd have a larger pattern.
You'd have expose a larger piece of the pattern, but you've got to think about the fact that these scattered radiation is coming off in directions like a cone.
Yes.
Okay? So if we move the film here now closer to the crystal, what we're doing is just exposing the lower angle beam.
Right, which would give you a smaller pattern, right? But I thought that the previous slide said opposite.
So what he's talking about is, so imagine all the dots on the film imagine they don't stop at a circle. Imagine they go out to
this is not a confining cone.
Okay.
So if you bring the detector closer to the crystal, then you're going to be collecting more of the high spots that were originally passing outside the edges of the film.
I see.
So you're going to collect higher resolution data. So you're right that the positions of the atoms are physically on further apart pixels, but you're collecting more of the pattern because you're closer to it.
Right.
So it's not like just a flashlight beam where you move it back, get a bigger circle.
Right.
Ah, no.
Yeah.
Okay, because these beams are basically coming off the crystal in all directions. Okay. So the film, at any given position, the film misses a lot of the pattern that escapes around it. Yeah. Yeah. So it's a bit of a misnomer when we talk about beams of X-rays. They're kind of wave, we're going to be thinking of them in terms of wave fields. But X-rays are generated, as was in the simple illustration of the Crookes tube. You essentially boil electrons off of a filament, like a tungsten light bulb filament. Those electrons are then accelerated by a large potential difference, a high voltage kilovolt voltage difference. They impinge on a metal target. Commonly used here is a copper target, so that the wavelengths that come off include strong rays at 1.54 angstroms, which corresponds to an energy level difference at the K shell of copper atoms. And of course, a lot of heat is generated, so there has to be a supply of cooling water to keep the anode from melting. But that's the simple principle of X-ray tubes, which were the same in 1912. So, Lowy and company, Friedrich and Knipping, his two younger assistants. I think one was a postdoc, the other was a PhD student, and I don't remember which was which. They didn't get the Nobel Prize. The boss did. Such is life. But Lowy did do, in principle, mathematical analysis and deduced these so-called Lowy conditions for diffraction. They observed diffraction only in certain directions, okay, so this was a discrete pattern recorded on these films, and the condition for having an exposure of the film was that the differences between the cosines of the angle of incidence and angle of scattering with respect to the three lattice directions needed to be integer number of wavelengths. And if it was a half integer number of wavelengths, there'd be no beam there. That was an unexposed part of the film, and so on. Bragg, well, this is a complicated picture because it's trying to consider all three directions at once, three-dimensional interpretation of the diffraction pattern. What Bragg realized, he knew all about this lattice geometry stuff. Lowy did not. He was another kind of physicist. He hadn't been thinking about the lattice structure of crystals or how you could build crystals by sphere stacking and so on. A lot of that kind of research was going on in England at the time, and going all the way back to Kepler's ideas. So Bragg realized that we don't have to consider these three independent or three different directions in the crystal. We can consider that the scattering of X-rays is like a mirror-like reflection off these lattice planes. That's a much simpler idea, so that the angle of scattering, theta, or the angle of incidence equaling the angle of scattering, theta, needed to be related in this way, that twice the interplanar d-spacing times the sine of that Bragg angle needed to be an integer number of wavelengths. And then we can rearrange this equation in several ways. But this factor n refers to the order of scattering. And then right after the Bragg equation, the Bragg condition, Bragg law was discovered, Charles Darwin, the grandson of the father of theory of evolution, deduced the formula that relates the intensities of the scattered beams to fundamental constants, charge on the electron, its mass, the square of the speed of light, the Q of the wavelength, the volume of the specimen crystal to the volume of the unit cell, and an absorption factor here because not all the X-rays go straight through the crystal, of course. And then these angle factors related to the scattering angle. And then finally to quantity that we'll spend a lot of time thinking about this semester, the crystal structure factor, the square of which is proportional to the intensities that can be measured from the scattered beam. This is not, these phenomena are not restricted only to X-rays. We can have diffraction by crystals of electron beams and or of neutron beams. The mechanism of the scattering is a little bit different. With respect to X-rays, it's an electromagnetic interaction between the X-ray beam and the electronic structure of the crystal. So it's essentially scattering by the electrons in the crystal. If we direct a beam of electrons at a crystal, the electron beam can also behave as a wave characteristic, so-called de Broglie matter waves, but again with a characteristic wavelength. And the scattering then takes place between the electrons and the electrostatic potential surrounding atoms. Right? So the outermost part of an atom is the electron cloud, so there would be a repulsive interaction between the incoming electrons in the beam and the electrons surrounding the atoms. Okay? So that gives the forces that are responsible for the scattering. And with respect to neutrons, again, also a de Broglie matter wave, but then it's the atomic nuclei. The neutrons pass right on through the electron clouds of the atoms and interact with the nuclei of atoms. But again, we have a different kind of scattering process, but all obeying Bragg's law. Because of the regularity of the lattice structure of the crystals, the arrangements of atoms. So whether we're talking about scattering from electrons, from electrostatic potential, or from atomic nuclei. And there's kind of nicely diagrammed. This was a very nice supplement some years back in Physics Today, which is kind of trade magazine that all members of the American Crystallography Association receive because of our affiliation with the American Institute of Physics. And this supplement was a very good discussion, and not just at this level, but a deeper discussion of neutron scattering in particular. Okay, diffraction. And we'll probably conclude this pretty quickly. So it goes back to observations made in the 17th century. We're worried about visible light diffraction now. This Jesuit priest, Grimaldi, in, I've forgotten which city he was in Italy, maybe in Florence, I don't recall. But he considered the problem of a beam of light passing, being limited by slits. Okay? So you don't, if you pass the beam of light through an aperture, you don't get a sharp image of the aperture. You see some additional illumination outside the projected image of the aperture. And furthermore, this illumination that occurred kind of outside the aperture limits broke the light up into colors. So there was a scattering of the light essentially by the edge of the apertures. So here we're illustrating, this one is not a motion picture, I don't think. No. So we have a plane wave of light falling on an aperture, and then most of the light that's recorded on a screen or a paper, whatever here, photographic film, it's, of course, brightest in the center, but then there are these secondary, weaker beams, so that the light spreads on passing through the aperture. And in the case of a single slit under more carefully measured conditions here with a laser, observed back in the 17th century, and the term diffraction was used from the Latin diffungere, to break into pieces. So here we see examples now of light passed through a single slit. But this is white light. So the different wavelengths of light get scattered through different angles. And then if one passes through a pair of slits, one gets a kind of, a sharper pattern than here. Okay? Different wavelengths scattered through different angles. And what you can see is that the longer wavelengths, the red, are scattered through wider angles than the short wavelengths, the blue. So the blue lines are are concentrated near the center of the exposure, but the red lines, it's a rainbow effect, scattered to wider angles. And here, if you can manage to get a monochromatic beam of light, so red light, you get a more open, with longer wavelength, you get a more open, diffuse scattering pattern just through a slit, and here, with shorter wavelength, blue light, a more compressed one, more concentrated one. Okay, so with respect to X-rays, we're worried about the same kinds of phenomena that have been observed with visible light, which is sitting in this region of the electromagnetic spectrum, let's say, with whether we want to look at energies or wavelengths or frequencies. So we're worried about X-rays, which are here in the much shorter wavelength region, okay? So, on the order of 10 to the -8 centimeters, okay? Gamma rays from atomic nuclei even shorter. And one does diffraction experiments with gamma rays as well, but that's not suitable for doing protein structural work. And we have to keep in mind, of course, this wave-particle duality of light, of electromagnetic radiation. We think of the light waves with colors in the visible region, depending on wavelength, okay, and related to their frequencies. But there is also the particle picture, where we're concerned with photon momenta, and typically photons are just illustrated in this squiggly line way. I mean, this could be a real recording of a light spectrum. These are artist's conception of a wiggly photon. So we'll stop here. To analyze these diffraction patterns, we resort to the Huygens principle, the wavelengths principle, which he enunciated in his 17th century treatise on light, that every point on the propagating wave front, of course he was concerned with water waves and light waves and so on, but every point on a propagating wave front acts as a source for a secondary wavelet. Right? So we can think of the wavefront being composed of this infinite number of adjacent points, which are points for the start of a spherical wave. And those secondary waves have the same wavelength as the incident, as the original propagating wavefront, and the same speed of propagation. And it's such that at some later time, after the wave front is moved on, the wave front then is just the envelope surface for all of those secondary wavelets. This is a case where a picture is really worth 1,000 words. So here's a picture from borrowed from Encyclopedia Britannica. So here we're considering plane wave fronts, and these points along this wave front A prime, each of these points then is a source for a spherical wave, and the with the same speed of propagation as the incident wave. Okay? If we consider a spherical wave, not a plane wave, the same principle applies, and the point is at the subsequent time, the envelope surface of those secondary wavelets, here curved and here straight, is the continuation of the advancing wave. Here it's illustrated as the wavefront A prime here is the first order scattering wavefront from these adjacent hypothetical spherical wave sources. So that from one to the next, so from here to here, so we have this spherical wavefront. Now here, let's advance a bit further. This second wavefront is one wavelength differ from the underlying one, 2 wavelengths, 3 wavelengths, and so on. And as the distance from these point sources increases, the curvature of these secondary wavelets, the curvature gets gentler, and pretty soon we're talking about a plane wave again. That's Huygens' notion about the behavior of light or water waves, and it goes back, goes on further until Thomas Young's famous experiment with 2-slit interference patterns. So he has here 2 point sources for light passing through a double slit, and he carries out this construction where the waves, when they fall crest on crest, we get, we build up a bright spot. When they fall crest on trough, a blank spot. And there another illustration of the same thing. So through a pair of slits, we get a pattern that looks like this if we expose, say, a photographic film. And there's another illustration of the same thing, which emphasizes that the condition for seeing crest on crest, crest on crest, crest on crest, seeing a bright spot out here, as well as here in the center, crest on crest, crest on crest. But over here, between, we're falling crest on trough. So there is negative interference here, constructive interference here, destructive interference here. And the condition for seeing these bright bands is that the angle at which those bands occur must be an integer number of wavelengths divided by the spacing between the two apertures. So again and again, we see this sine theta being related to an integer number of wavelengths. Of course, Bragg the Younger knew all about this kind of wave physics when he was thinking of, when he devised Bragg's law for thinking of the diffraction effects as specular reflection effects. Here again, 2 different illustrations, single slit, double slit, and bright and dark, bright and dark. And here just an illustration of that d sine theta business. If we're considering from this pair of slits, we're looking at what comes off in this direction, then if this is the angle theta away from the center direction, then that angle theta also appears in this little triangle, and the difference in path lengths for this beam as opposed to this beam is d sine theta. Okay? So we need the path length difference to be an integer number of wavelengths. Oh, and that's telling us the same thing. So here we'll stop for today and take up on this, looking more at, a little bit more at optical diffraction, and then get into more of X-ray diffraction starting on Tuesday. So I'll try to get this set of slides up where you have access to them on the FTPs. So thank you.